Let's pick up our conversation of operator overloading, starting with why we actually need operator overloading. So we're quite accustomed to access arrays and vectors using indexing and the square bracket or the subscript operator. It would make sense that we'd want to do this for our own grocery list objects as well. As you can see, in main, we instantiated a grocery list called shopping, we add items to it, and then we want to print out the first item on our list. So at position 0, when we call get on our shopping object, it works perfectly well because we just defined that member function and implemented it. But when we try to use the square bracket operator, the subscript operator on our shopping object with index 0, it will not compile. And the reason for that is that C++ doesn't know how that operator should work on our grocery list until we tell it. And we do that by implementing how this operator should work for our grocery list class. And that's a very good thing because there's no assumptions about how operators should work on classes that you define. You just have to define those operators for yourself. And just to refresh our memory, recall that a signature of a function is the name and the number of types of arguments, and every function must have a unique signature. So here we have 5 functions with unique signatures, and they're all named f1. So we have f1 with an integer parameter, with 2 integers, with a double and an int, and then a list of integers. So in this regard, we say that f1 is overloaded. Now we can also overload operators. So C++ defines operators for us, such as plus, multiplication, equals, for basic types such as strings and doubles and ints. But now we want to think about what should these same operators mean for classes that we write. So for our grocery list, we'd want an operator to add 2 grocery lists together. And the logical assumption might be to, if we want to add list 1 and list 2 together, we would concatenate them, or basically take all the items in list 2 and add them to the end of L1, similar to what we had done with merge. But there's no assumptions made about that that's how it should work until we actually implement that operator. Similarly, on the user class here, we have a user who has private data, which is the ID and the name used to identify the user. And we want to think about what should equal mean for a user. So one possible interpretation of what the equals operator could mean for a user is if they have the same name, as we have in option 2 in main. So if user 1 and user 2 have the same name, then they're equal. But it might have made just as much sense to implement equal to be if they have the same ID. So you can see there's no assumptions about what this operator should mean for classes that you make, and you have to decide what these operators should be, should you choose to implement them. Now we're going to see that there are 2 approaches to implementing operators that when you're overloading them. One is as a global function and the other as a member function, and the decision of whether it's a global function or if it's a member function will depend on the left-hand side object and the right-hand side object of the operators, and we'll get to this more specifically as we work through examples. But first, let's look at when we're going to implement them as global functions. So inside main, we have an hour and a suffix string, and we want to be able to create another string called the time, which is the concatenation of the hour and the suffix. Now, this won't compile unless we actually define an operator for what it means to add an integer on the left-hand side to a string. So you'll notice that the object to the left of the operator plus is the left-hand side, and to the right is called the right-hand side. So the compiler is looking for a function with the name operator plus, and operator plus is whenever you want to implement the operator, you have to use the operator keyword and then the actual symbol for the operator. So that's the name of the function. And this function has to take as the left-hand side input an integer, and as the right-hand side, a string, which is interpreted to be the suffix. And you can see it just uses a string stream to actually construct the string, which is the time as we would expect it, the hour followed by the suffix, AM or PM, and then just returns the string, which is then saved in main, and then we can print it out. So this is an example of how we can implement this as a global function. You'll notice that this operator plus is not the part of any class. It's just a function that we wrote. Another definition of the operator plus function given when the left-hand side is an integer and the right-hand side is a string. So now let's think about what happens with our class. So now we're going to be developing a complex number class. And you'll notice that it's not very good because everything is public in this class right now. So we have the constructors, we have to get the real component and the imaginary component, and then we just have doubles for the real and the imaginary components, but they're all public. So when they're all public and you want to add two complex number objects, we can just use a global function. So you may notice in main, we create two complex number objects, C1, C2, and then we want to add C1 and C2 together and save the resultant 3. When C++ sees this statement, it is actually looking for a function that is called operator plus that takes as its arguments, the left-hand side is a complex number and the right-hand side is a complex number, and it returns a complex number. So this is what we've implemented here. So we have the function called operator plus, and it takes as the left-hand side parameter a complex number and the right-hand side parameter as a complex number. Then it creates a local complex number. It adds the real parts of the arguments, it adds the imaginary parts of the arguments, and just returns this complex number, which is the sum, and then you print it. So this worked perfectly fine because everything in our complex class is public. And this is an example of poor encapsulation. We're not protecting the data of our complex number at all. So a better way to actually represent this class is to make our data private. And that's what we have in this example here. So we make our real and our imaginary doubles, representing the real and the imaginary part of the complex number, private. But as you can imagine, once we make our data private, so now we're protecting our data of the complex object, now we have a problem with how we had implemented this as a global function. And the problem isn't with the compiler. So the compiler is looking, as before, we created C1, C2. It's looking for an operator that can take as the left-hand side and the right-hand side complex number. But now the issue is actually inside the implementation. So this function is completely what we're looking for, but now because the data is now private, this function can no longer access the private data members of any complex object. So that's the problem. The compiler will now be complaining that you cannot access real or imaginary for any complex number. So this leads us to why we may need to consider when we want to make these member functions.